All right, well, today we're going to finish up growth of functions, and I think we'll have time to start some theory of integers. Well, I guess I'm going to have to stay on this side of the room. All right, we're going to start today by, at the end of class last time, check this out, G.6, we talked about that this is a theorem. And what I want to do is give you an example, a specific example of the interpretation of big theta. So here we go. This is an interpretation. Interpretation of the following fact. 2n squared plus 1 equals big theta of n squared. All right, so this. Now, last time we defined big O and big omega, right? Big O was the upper bound, big omega is the lower bound. And then big theta says that it's both an upper bound and a lower bound. And then we just talked about this theorem, G.6. Big theta of G dot n is the set of functions. And then there you have the set of it's a set of all the functions in the range, and then you have in this range there exists a C1, C2, N naught, and so on. Now, so in this particular case, what I want to do is give you a graphical interpretation of this particular case. So check this out, sports fans. What we have, suppose here we have, so here we're plotting n on this one, and then we're going to plot 2n squared, and we're going to do we're going to plot some functions of n on the y-axis here. So this is going to be 0, this is 1, this is 2, this is 3, this is 4, and so on. Okay, and I'm going to stretch out the scale a little bit here. So here is going to be 1 on the n-axis. All right. Now, do you remember last time we said that we showed a c, I don't know if you have your notes there. We showed there was a positive c and so on. For 2n squared plus 1 is big theta of n squared. Yeah. So n naught, so this is going to be our 1. Now, so here what we're going to do is we're going to graph 3 functions. First of all, let's graph 2n squared. Okay, 2n squared. So what's the y-intercept? 2n squared. 0. 2n squared. It'd go through 0. And at 1, where is 2n squared? 2. So does everybody understand that it's a parabola that goes through here?
So we're not adding 1?
No. We're going to do that later. Okay. So 2n squared is going to be a parabola that goes through here. So it's going to look like something like that. Is everybody with me on this one? Mm-hmm. And now what about 3n squared? If we graph 3n squared, what will that be? That'll also go through the origin.
But at 1 it'll be 3.
But at 1 it'll be 3. So that'll come up through here, right? Roughly here. So it'll be a parabola that looks like this. Is everybody good with that? Parabolic? Okay. And now, okay, so this is, so here's our 2n squared, and here's our 3n squared, okay? And now let's do 2n squared plus 1. Well, now what's 2n squared plus 1 going to look like? It's going to be also a parabola.
It's up 1, but it goes through 1.
It's up 1 here, but it goes through, wait, when n is 1, it's 3? Yeah, so it's also going to go through here, right? But it's going to start here. Right? So basically what it's going to do is it's going to start here and it's going to do something like this. Now, is everybody with me on this? So let's take a look at the regions. Let's take a look at this. Where n is 1 here, 2n squared plus 1 starts out outside this envelope. But do you see what happens is for n greater than or equal to 1, what happens is 3n squared is an upper bound of 2n squared plus 1, and 2n squared is a lower bound of 2n squared plus 1. Is everybody clear on that? So here, this is 2n squared plus 1. And so what we're saying is that in this region, here, 2n squared plus 1 is bounded above by a c times n squared, and it's also bounded below by a c times 2n squared. But they're different c's, okay? So let's write that out. 3n squared is an upper bound. 3n squared is an upper bound of 2n squared plus 1. So that means that's big O of n squared, right? But then 2n squared is a lower bound of 2n squared plus 1. So that's big omega of n squared. And so our interpretation according to G.6, what we have is the following. We have 2n squared is less than or equal to 2n squared plus 1, 2n squared plus 1, which is less than or equal to 3n squared. But that's only true for n greater than or equal to what? 1. For n greater than or equal to 1. So basically what we're saying then is that we've identified these, look, we've identified the C1 and the C2 and the n naught in G.6. So you see this is the, here's the C1, this is the C2, and this is the n naught. So this is the C1, this is the C2, and this is the n naught. Are you with me? And in this particular case, in this particular example, this 2n squared plus 1, we have found both an upper bound and a lower bound for it, and it's the same function, okay? It's just that when you have a different, you need a different constant for it to be an upper bound and a different constant for it to be a lower bound. But given that those constants exist, such that, you know, it's bounded both above and below, what that means is that in this envelope, you know, between the upper bound and the lower bound, with a constant, it's bounded above and below. So we know, and so that's the most we know. So we know a lot about the asymptotic behavior of 2n squared plus 1. Now what's really interesting in the study of algorithms is that when you get into really complex algorithms, sometimes researchers will know that a particular algorithm is bounded above by some function, and the one that is bounded below is not the same function. So we don't know what its big theta is. Yeah, I mean, you see what I'm saying? So it's possible in some complicated algorithms, and when you do analysis of algorithms, and you know at a really advanced level, you might not know what the big theta is, but you might know a big O, so you'll know an upper bound, and you might know a big omega, a lower bound, but they won't be the same. They won't be the same thing. And so researchers say, oh, you know, they'll investigate, do a mathematical analysis, and they'll say, oh, I was able to lower the upper bound, or I was able to raise the lower bound, so we know more precisely how this algorithm behaves for how it grows for large problems. All right, does everybody get that? Okay. Now there's one more concept that I want to point out here in this particular example. All right, and now let me ask you this. What about 2n squared plus 1? Here, tell me yes or no on this. 2n squared plus 1 equals big O of n cubed. Now my question to you is this true or false? It is true, because after all, if you, n cubed goes up way faster than n squared, right? So I mean, if it's bounded above by n squared, for sure it's bounded above by n cubed, right? And what about this? 2n squared plus 1 is big omega of n. Is that also true?
No. Sorry, I thought it was O. So that is true.
Yeah, and this is true also. So both of these are true. So both are true, okay, but not so useful. You know, because what happens is, if you know that it's bounded below by n squared, well, that's not saying, I mean, it's not saying a whole lot that it's bounded below by n. You know, you're saying more when you say it's bounded below by a bigger function. You see what I mean? So even though these are true, they're not as useful as the fact that, as the bounds that we did prove, that the upper bound and the lower bound that we did prove. All right? Is everybody clear with that? Now, there's one more technique. Now, last time we did an example, or we did lots of examples. I think we did 4 different examples of proving upper bounds and lower bounds. But there's one tricky case where that I need to show you how to deal with it, because it's kind of rare that it comes up, but it does come up occasionally. And so we need to know how to deal with it. And so I'm going to start. So we're going to prove a lower bound. We're going to prove a lower bound, but I need to make a statement here first. N naught is an integer, okay? Because it's usually like n is usually. I mean, we draw it continuously and we analyze it continuously, but you know, in real life, it's like the number of data points or the number of, it's some measure of the size of the problem that you're dealing with. And it usually has to do with the number of data points, okay, that you're analyzing, okay. And what did we say about n naught and c? They both had to be what? Positive. They both had to be positive. Now, for n naught to be an integer, that means, you know, it has to be 1 or 2 or 3, right? So n naught can't be less than 1, but it might happen that c, even though it has to be positive, you might have to make it be less than 1. So n naught is an integer, but c can be less than 1. Now, here's the thing. It can't be less than 0. Are you with me? It's got to be positive, but sometimes you have to make it less than 1 in order to solve the problem. And here is an example. Prove, what we're going to do here is we're going to prove that n to the 4th minus 100n minus 23 equals big omega of n to the 4th. All right? So what must we show? Well, we always have to write down what we must show. Must show what? Positive c and n naught, such that what? And then what's the inequality we have to prove? Now, this is the upper bound or lower bound?
It's a lower bound. So
It's a lower bound. 4 n greater than or equal to
1.
No. Well, I mean in general, but for n greater than or equal to, we have to show a c and an n naught such that this is less than c times n for n greater than or equal to n naught. Are we good? Yeah, that's always the program.
Do we always do that?
Yeah, we always do this.
Because I don't have that in my notes.
Yeah, well, you should. Yeah, it's always for n greater than or equal to n naught, because those we have to show c and n naught such that this statement is true. So as usual, we'll start this way. We'll go n to the 4th. So here's the proof. So we'll start with n to the 4th minus 100n minus 23. And now what we have to do is we've got to get this to be greater than or equal to, you know, we got to have some equals and some greater than or equal to's along here, right? Because now, watch this. This is greater than or equal to, now, do you agree that if I subtract something from this,
It'll always be greater than whatever.
that this will be greater than or equal to whatever I get by subtracting? Now watch this. We have 100 here, and we have a 23 here. Now this might seem like I'm pulling a rabbit out of a hat, and in fact I am. I'm going to subtract 77. All right? Do you agree that if I subtract 77 from this, that this will be greater than or equal to this? Well, if I subtract 77 from this, what do I get? N to the fourth minus 100n minus 100. All right? Now, what I'm going to claim now is that I'm going to claim that this is greater than or equal to n to the fourth minus 100n minus 100n. Okay, now when is this true? Do you agree that this is true?
Yes.
But when, under what circumstances? In order for this to be true, what has to happen? How could this be greater than or equal to this? Are we subtracting more from this?
Yes, you're subtracting one, as long as n is positive.
Yes, because n is greater than or equal to 0.
Well, greater than or equal to 0 or greater than or equal to 1?
Greater than or equal to 1, because n is greater than 0.
Yeah, okay, so this is provided.
N is positive.
Actually, if n were less than 1, you'd be subtracting.
You'd be adding.
Yeah, well, I mean, it wouldn't be greater than, well, anyway.
Yeah, if it was greater than or equal to, you'd be subtracting 0. It'd still be greater than or equal to.
Provided n is greater than or equal to 1. Does everybody agree here? So this equals by math what?
Minus 201.
N to the fourth minus 200n, right? Okay. And now let's factor out an n. And so that's going to be n. So how do you factor out an n? What do we get? N cubed minus 200. Yeah? Are we good? Now comes the big technique. Actually, let's go over to the other side to finish this off. I claim. Now, what do we, actually here, let's see, before we claim anything, let's see what we're trying to do. We have to get this to be what? Greater than or equal to c times n to the fourth.
Right.
How are we going to do that? Can I just drop the 200? Can I say this is greater than, I can't just drop the 200, right? Because that's going the wrong way.
But you're saying, you're saying c is less than 1.
Yeah, the only way that we can do this, yeah, you see it's going the wrong way for us to drop this because of the negative sign. Are you with me on that? Okay, so coming over here. So here's what I'm going to claim. Now watch this. We're going to claim this is greater, I'm going to claim this is greater than or equal to. Now, for here, right here, for the rationale, leave, a couple or 3 lines here because this is going to be a big, we're going to do some arithmetic, some math in here, all right? I'm going to claim that this is greater than or equal to n times, now watch this, 0.5 n cubed. Now look, you guys. In other words, I'm claiming that this is greater than, that will work provided what? This is what? this n cubed minus 200 is greater than or equal to what?
1.
No. Yeah, 0.5 n cubed. Now, is everybody clear on that? That is greater than or equal to this, provided what? So this is provided what? What did you say, Alex? N cubed, yes, n cubed minus 200 is greater than or equal to 0.5 n cubed. Now, does everybody see why that would be? Because, I mean, it's just times n, right? So provided that n cubed plus minus 200 is greater than or equal to 0.5 n cubed, that is greater than or equal to this, right? But now look, in this proviso, we can do some math now. Because in order for this to be true, so how can we do math on this? We could take what? Take this over to this side, are you with me? And then take this 200 over to the other side, and what will we have? So this will be n cubed, what? Minus a half n cubed. So that'll be, no. N cubed minus a half of n cubed is half of an n cubed, right? So this is going to be 0.5 n cubed is greater than or equal to what? 200, which means that if we double both of these, right, that means n cubed is what? Greater than or equal to 400, which means that what?
400 minus 200 is positive.
Well, no, which means that n is greater than or equal to, because we want to find out, we want to get our n naught here. So, which means that what? N is what? Greater than or equal to the what? The cube root of 400, whatever that is. Well, but we could work that out on a calculator, right? And it's positive. Yeah? So does everybody agree then, by virtue of the way we set it up, that is greater than or equal to this, provided n is greater than or equal to the cube root of 400, right? But now we're home free, right? This equals what? What do we want to get this eventually down to? C. We want to get it down to what? C.
Well, 0.5 and n.
Yeah, but what do we want to get it down to? C times
So you're just skipping.
n to the fourth, right? But now it'll be this provided what? This will equal this provided what? Yeah. Provided C equals 0.5. So therefore, C equals 0.5 and naught equals what?
Then a greater.
The cube root of 400. And boom, we proved it. Because we showed that there exists. We showed the existence of these two numbers, C and n naught. But in order to do that, you had to make, the technique for doing this, when you have a negative, when you have a power here and then you have a negative here and you want to do a lower bound, sometimes the only way to do it is to have C be a half. I mean, you could have made it a third. You could have had it be a third and then you would have had a different C and an n naught,
C's don't have to be integers?
Correct, they do not. They just have to be positive constants. They do have to be greater than 0, but they don't have to be greater than 1. In fact, sometimes they can't be greater than 1. All right? So that's just a tricky situation that sometimes comes up in the proof in these upper bound, lower bound proofs. And this is a technique for how you can, I showed you this technique for how you can do
So
it.
is n not technically an integer?
Well, that's a good point. What you would do, that's a good, because the cube root of 4, it's not an integer. So what you would do is it would be the ceiling. It would be, because it has to be an integer. Because, I mean, if it's greater than or equal to this number that has a fractional part, then for sure, I mean, if it's greater than or equal to one that is bigger than that, the integer bigger than that, so you could round up, So to be strictly, accurate, you could round up. All right, now let's take a look at the next section here. Now, these are, let's take a look at G7. Okay, comparison of functions. First of all, we have some really interesting properties, but I think you can see what they are. First of all, f dot n is big O of f dot n. In other words, a function is its own upper bound, right? And a function is its own lower bound. It's also big omega of f dot n. And it's also a big theta of itself, right? Because these are, remember, the inequalities are less than or equal to, greater than or equal to. So if it's equal to it, then, a function is its own bound. Like n squared, an example of this would be n squared is big O of n squared. I mean, that's trivial to prove, right? Okay, and we also have symmetry. If f dot n is big theta of g dot n, if it's bounded above and below by g dot n, then g dot n is big theta of f dot n. But that only works for theta. That doesn't work for...
That's when the upper bound and lower bounds are identical anyway.
Yes, that's when upper bounds and lower... And if the upper bounds and lower bounds are not identical, then G.9 tells us that we have what's called transpose symmetry. In other words, if f dot n is bounded above by g dot n, then g dot n, or if and only if, it's not if then, it's if and only if g dot n is what? Bounded below by f dot n, right? And those things are easy to prove. Is everybody clear on that? And then we have some interesting transitivities. And these are kind of easy to see. If f dot n is bounded, now what is a, G.10a, if f dot n is bounded how? Above or below? In A. So if f dot n is bounded above by g dot n, all right, and g dot n is bounded above by h dot n, then what? F dot n is bounded above by h dot n, right? So you can think of that as bigger than, are you with me? And the same way for lower. If f dot n is bounded below by g dot n and g dot n is bounded below by h dot n, then f dot n is bounded below by h dot n. And then if it's exact, if f dot n equals big theta of g dot n and g dot n equals big theta of h dot n, then f dot n,
We're all three the same.
yeah. All right? So those are just sort of intuitive. We can understand the truth of that just intuitively. All that makes intuitive sense when you understand the concept of upper bound and lower bound.
So when we prove big theta, we have to prove that there exists an upper bound and a lower bound.
Yes, that's the way you do it. You prove that whenever I ask you to prove big theta, what you have to do is you have to do it in two steps. First prove big O and then prove big omega, and then you've done it.
And they have to equal each other, right?
No, the bounds don't. I mean, no, it's a separate proof. What do you mean they have to equal each other?
The omega and the big O for theta to work, or no?
The g has to be the same. Like if I say,
Like big O has to be n squared and omega has to be n squared, and that's when.
yeah, and that's when the big theta is n squared.
Okay.
Yeah. That n squared is the same on both. Yeah. So you show that it has the same it's bounded above by the same function, then it's bounded below by, then it's big theta of that. Actually, before I do this next example, there's now, you're not going to like this. Because check this out. We've been doing, all of the examples that we've been doing so far have been examples with polynomials. But I mean, there are other functions. In particular, the log base 2 function comes into play a lot with analysis of algorithms. And but in the case where we have a polynomial function, and check what this is. Define an asymptotically positive polynomial p dot n of degree d to be p dot n equals the sum on I, 0 less than or equal to I less than or equal to d of a sub I times n to the I. So suppose it's like this. 5, give you an example, 5n to the, let's say 5n to the 6th minus 2n to the 5th plus 4n squared plus 93n minus 16. I claim that this is an asymptotically positive polynomial. Asymptotically positive polynomial. Now, why is it an asymptotically positive polynomial? Because it's in this form, and these constants are all coefficients, and furthermore, this one is what? What do you know about this what do you know about this a sub? What is this a? This is a sub 6, right? This is a sub 6, this is a sub 5, this is a sub 2, this is a sub 1. Are you with me? And furthermore, this a sub 6 is positive. The first one has to be positive. These can be positive or negative, right? So here a sub 5 is less than 0. But still, as long as this one's positive. And what does this theorem say?
That function is...
That this, the theorem says this function is big theta of what? N to the 6th, right off the bat. Is all you have to do is, if it's a polynomial, is all you have to do is make sure that this is positive, and whether this is plus or minus, boom, it's
like L'Hopital's rule.
Yeah, well, I mean, you can prove this using these techniques.
Isn't L'Hopital's routine the derivative?
Well, I mean, just like the mindset of looking at it.
Of looking at it and seeing what it, yeah. Okay, now, but whenever I ask you to prove something's big O or big omega, it's illegal for you to say by G.11 it's big theta of n.
Why?
Because I want you to be able to prove the individual. I want you to be able to prove it directly by the direct definition, not by using this theorem.
Okay.
All right? Because actually, knowing how to do that is basically how you prove this. You do it in general. You just do it in general. So you need to know how to do it specifically. All right? But just to let you know. All right. Now, the very last thing then I want to do with this material is let's take a look at G.12. That's the last theorem. No, G.11 is not a definition. No, the definition is the definition of an asymptotically positive polynomial. The theorem is that it is big theta of n to the d. That's the theorem that you can prove from the definition of big theta. But we're not going to take time to prove it in general. All right? Now, I want to give you an example of G12. Now, do you remember when we said big O of 1 is a set? These are sets, right? So what this says is that and what is this symbol here for, what is it? Proper subset. So big O of 1 is a proper subset of big O of log n. That LG is log base 2. All right. And that's, in turn, is a proper subset of big O of n, which is in turn a proper subset of big O of n log n, which in turn is a proper subset of big O of n squared, which is in turn is a proper subset of big O n cubed, which is a big proper subset of big O of 2 to the n. All right. Now, what this says is that because they're proper subsets, that means there must be something in. Let me see which one. This is the smallest one, right? There must be something that's in this one that's not in this one.
Right.
All right. So let me give you an example. Let's suppose so this is a G.12 example. I'm going to write down 4 relationships. 2n squared plus 1 is big O of n squared. Do you agree with that? Is it bounded below? All right, and how about this? 2n squared plus 1 is big O of n cubed. Do you agree with that?
Yes.
Because it's bounded above, if it's bounded above by n squared, for sure it's bounded above by n cubed, right? And how about 4n cubed plus 5? 4n cubed plus 5 is big O of n squared. Now, is this true or false?
False.
That's false. So we'll say that's not. Are you with me?
Not the case.
Not the case. And how about 4n cubed plus 5 being big O of n cubed? Is that true? That's true. Okay, so look, so if we take a look at this on a Venn diagram, it looks like this. So here's the set of all the ones that are in big O of n cubed. Are you with me? And here, and what is this saying? Let's go back up here to G12. This says that big O of n, this says big O of n squared is a proper subset of big O of n
Means
cubed.
all of O of n squared
Is inside. Yes. So,
Big, small ring and then bigger rings.
yeah. So this is big O of n squared, right? Now I want you to tell me, where should I put the point? Where should we put the point for the function 2n squared plus 1? Is 2n squared plus 1 in this set?
Yes.
Is 2n squared plus 1 in this set?
Yeah.
So does everybody see then that 2n squared plus 1 should be here, right? But now what about 4n cubed plus 5? Is 4n cubed plus 5 in this set?
Yeah.
But is 4n cubed plus 5 in this set?
No.
No, so that one's out here. Are you with me? So this one is the 4n cubed plus 5. Right? So, I mean, these really are sets. Even though we say equals, you know, like we said last time, equals is, we should be saying is an element of. But, and of course, this works the other way around. What about 2n, what about here? Let's do 2n squared plus 1 is, yeah, these should be elements of instead of equals, but whatever. Equals big omega of n squared. Is that true? Is this bounded above? Sorry, is this bounded below by n squared?
Yes.
Yeah, okay. And how about 2n squared plus 1 equals big omega of n cubed? How about that one? That one's false, right? So we got to make, that's not there, right? And then how about 4n cubed plus 5 is big omega of n squared? Is that true?
Yes.
Of n squared. And how about 4n cubed plus 5 is big omega of n cubed? Is that true?
Yes.
Yeah. Okay. So now what is this? But now what is it saying about the big omegas? Which one is outside and which one, you know? Yeah. Yeah. So this one is big omega of n squared, whereas this one is big omega of n cubed. Right? And so where are our points? Where is the 4n squared plus 5? Is it in this one?
4n cubed plus 5 is in the middle.
Yeah, this time the 4n cubed plus 5 is here. So here's the 4n cubed plus 5. Whereas this one's going to be the 2n squared plus 1, right? Okay, so that's what that means. Now, you know, let's take a look. There's one more thing I want to point out before we go on. And that is, do you see why? Now, check this out. On A, do you see that here we have 1, and here we have log n. 1 is a subset of big O log n, which in turn is less than, let's just think of it as being less than. 1 is less than log n, which is less than n. So do you see that log n is between n and 1, is between 1 and n. All right? And now furthermore, now let's take a look. Here, this one's n, and this one's n squared. Now why would n log n be between n and n squared? Because n squared is n times n,
And log n is less.
and then log n is less than n, so that's why n log n is less than n squared. So actually, there's another one we didn't do it here, but
Log in n squared.
there's actually, what's between n squared and n cubed?
N squared and log n.
Yeah, n squared log n is in between, but we just didn't show it. But that's true, and it's similarly all the way up. Are we good? I mean, so that's how you can think about that n log
Would
n.
n to the fourth be in comparison to 2 to the n?
Oh, wait, 2 to the n is way, that's exponential. That's way, yeah, that's of any polynomial. That's beyond polynomial.
That's true.
Yeah, that's beyond polynomial. All right?
But yeah.
Okay, and these are really important. In data structures, I mean, we're gonna run across this. You're gonna run across this just a bazillion times in the future, because anytime you do an analysis of algorithms to find out how fast your program runs, for very large data sets, for when n is really big, so when asymptotically large, you always want to know whether it is like an n squared algorithm. By the way, have you guys done like sorting?
Somewhat, yeah.
Yeah, okay, and so some searches take our order n. If you want to search through, if you have twice as many things to search through, it'll take you twice as long. But some searches take only log n, like a binary search only takes log n.
If it's already sorted.
If it's already sorted, and you can cut it. So you might have run across this in your.
Yeah, we've talked about big O, but not
Yeah.
big omega.
Yeah. Okay. So anyway, that's very. All right. Well, we have a few minutes. I think it doesn't hurt to introduce a new topic. So now we're going to go on. We're finished with the section G, and we're going to go on to chapter 15. Now, here's the thing about chapter 15. Our author does a really thorough job of describing a theory of integers, okay? But I'm telling you, and I used to try to plow through this material, but it's just, it's just tedious and it's uninteresting because it's so elementary. I mean, so what we're going to do is we're just going to jump right into the middle. We're just going to jump right in. We're just going to jump right into the middle of the chapter because we don't have time to. If you're interested in doing this, you can. And I used to have my equation sheet used to have all the theorems up. We're starting at 1553. Good grief! There's 52 theorems and definitions and axioms, but they're all just really easy stuff that you learned in algebra. And so I'm not gonna, it's just boring and it's pretty elementary. But it's good that it's there. If it's there, if you need it, if you want to refer back to it. We're going to start right in with 53, and we're going to start in by defining minimum and maximum. Okay. So let me do some examples. And we've seen this notation before, up and down. I think somebody called it the up and the down operator. But anyway, 1553 examples. Okay, so so tell me this. The down arrow means min. 5 min 7 equals what? 5. Okay, and how about -3 min -4? What does that equal? -4. Okay, and 5 max 7 is what? 7. And -3 max -4 is -3. Okay, so everyone understands that. Now, what about the identity? So this is a binary operator, right? What about the identity? Is there an integer I? Is there an integer I such that, now how does the identity work? Such that x, how does the identity for addition work? X plus 0 equals equals x. So is there an identity I such that x max I equals what?
X.
Equals x
I less than
for all x.
I less than x.
No, there has to be a number, a constant.
For all x what then?
For all x, such that x max I equals x for all x.
No. No, there isn't.
You're right, there isn't. So therefore, this operator has no what?
Identity.
No, yeah. So the answer is no. Okay? So there is no, okay, so Max has no identity. But wait a minute. If Max has no identity, we're up the creek, right? Because what is, because what does 813 say? Axiom 813. Do you remember what 813 was?
It equals the empty range when, or
Yeah. Here, let's look at 813. Axiom empty range. Star x range false is u, where u is the what? Identity for that. But wait, that means that this is not a what? What does it have to be in order? Max is not a what? Yeah, what does it have to be able to quantify? Remember? Starts with an A. It's AM. Remember this?
That's a weird word.
Yeah, it is a real one.
Kyle would remember.
Kyle would remember it. I am an abelian monoid. It's not a what? It's not an abelian monoid. Okay, so, all right, so here's the thing. Because it's not an abelian monoid, that means strictly speaking, we can't quantify it. But we're going to quantify it anyway.
Oh no.
But under these restrictions, okay? So look at our restrictions here. It says, although min and max are symmetric and associative, they do not have identities over integers. Therefore, axiom 8.13, empty range does not apply to min or max. Also, when you use the range split axioms, none of the ranges can be false. So as long as you have these restrictions, you can do it. So we're going to do it, but recognize that not all of our theorems apply. All right, but other than that, it's just too convenient. It's just too convenient to have it be otherwise. All right. So now let's take a look, and so we'll start next time with taking a look at the definition of min and max. Because look at the definition of min and max. Definition of min is for all z, etc., and definition of max is for all z, whatever, right? And then
It's weird that you use itself in its definition.
yeah, this is a weird definition. In fact, it's going to the way we prove things is going to be a little bit, theorems is going to be a little bit different because of the way of what this definition is. In other words, this does not say x min y equals something. So you can't say, well, if it equal, instead it's a quantified expression that's either true or false. Yeah. All right, so we'll take this up again. And fortunately, you didn't have any homework due today, right? So you'll have some, for Monday, you'll have some growth of functions problems. All right, see you next time.